So the topic of my report representation is numerical study on the influence of the water mist boundary on the detonation propagation characteristics in semi-confined channel. Okay. So I will give my presentation in these 4 parts. Part 1, the research background. Detonation is an extreme combustion mode in which the leading shock wave is strongly coupled with reaction region. We can see 3 pictures here. Picture one is a rotating detonation engine. We can see the lateral expansion phenomena here, like the line 4 or line 5. And picture 2 is a typical experiment result of layered detonation. The detonation wave is confined by the inner gas. And picture 3 is a simulation of lateral expansion. Now there are some previous studies about semi-confined detonation. It can be seen that there have been many researches about the detonation in semi-confined channels at present. The pictures above are the experiment and simulation studies of lateral expansion phenomena. And now we can see the RDE's combustion products contains moisture, which may turn into the water droplets during the operation. Therefore, it is necessary to conduct research on the propagation characteristics of semi-confined detonation with water mist at the boundary. So here's part 2, numerical method. Our calculate software is DeepFlame, which is a new compute platform based on the OpenFOAM. And our solver is DFCDS form. We use compressive reactivity NS equation to do the calculate and Euler-Lagrangian method for gas-liquid two-phase coupling. And here is the computation model. It's a 2D model. The constraint layer is water mist with air. The reaction is xylene and air premixed gas. The boundary condition is the left and lower phases were set as wall reflections, and the upper and right were set as non-reflective exists. Now here is the verification of the solver. The comparison between the current simulation results and the reference results proved the reliability of the solver. And this is the grand independence verification. We made 3 kinds of grand size. The result shows that the second size set of grand can balance computational resource and accuracy, so it was used in this study. Now here's part 3, results and discussion. Here is a comparison of cell images between the air constraint layer and water mist constraint layer. You can see that water mist constraints are easier to extinguish. From the perspective of cell development, it can be divided into 4 detonation phases. They are the cell disappearance, cell recovery, large cell propagation, and cell extinction. And in the end of both cases, no downward triple points were formed, resulting in final extinction. So we can see that the formation of downward moving triple points at the gas interface is the key of self-substanting propagation of detonation. Now here's the comparison of temperature distribution. We can also see the droplets distribution at here. Now, the interaction between the detonation wave and the interface forming an oblique shock wave in both cases. Under the constraint of water mist, a low temperature zone appears behind the slap line due to the evaporation and heat absorption of liquid droplets. And from the instantaneous velocity, like this picture, it can be seen that the detonation propagation speed significantly reduces during the large cell propagation stage, which means that the intensity of leading shock wave mainly decreases here. Now the red pictures are the pressure distribution and the temperature distribution at different stages. The droplet distribution is also superimposed here. Now we can see during the propagation process of water mist constraint, the number of transverse waves gradually decreases, and the interface deflection angle gradually increases. Then in the propagation process, the distance required for droplet evaporation increases. And here's under the pictures is the average heat release rate at different stages. We can see that the average evaporation rate droplets is highest during the cell recovery stage, while the lowest is the cell failure stage. At stage 4, the intensity of flame near the slump line is not enough to quickly evaporate the droplets. And now here pictures showing the interaction between transverse waves and the lower wall or the upper confined layer, respectively. We can see that at 1.1 millisecond, a downward moving triple point and a transverse wave can be observed. And at 1.12 millisecond, the downward transverse wave reflects off the wall surface and forms a new triple point at 1.14 millisecond. And for another type, at 1.2 millisecond, a downward moving transverse wave propagates to the mist interface. As the Mach stem interacts with the constraint interface, at 1.22 millisecond, the Mach stem bends and forms the new triple points at 1.24 millisecond. And then we made a polar curve analysis of the reaction pressure from water mist constraint layer. We can see that at 1.2 millisecond, it can be observed that the polar curves of the reflected wave and the oblique shock wave intersect, and the reflected wave adheres to the interface without forming a new Mach stem or generating a new triple point. And at 1.22 millisecond, the velocity of detonation wave decays, and the wave's angle with the interface increases. Finally, the polar curves of the reflected wave and the oblique shock wave no longer intersect, resulting in Mach reflection and the formation of a new Mach stem. So, therefore, whether Mach reflection can occur is the key to formation of new triple points at the interface. And then, when we made a study to change the temperature of water mist constraint layer, we tried 500 kelvins and 1 kilokelvins. Now we can see when the temperature of water mist constraint layer is increased, the propagation distance of the detonation increases, and the self-substanting propagation can be enhanced. And that's why there's no cell failure stage here. And this result is correspond with the research conclusions under the condition of no water mist. And we can see the higher the temperature of constraint layer, the more regular that cell development process, and higher stability of detonation wave propagation. Then, for all three temperatures, we select the moment when the detonation wave is in the stage of large cell propagation and shown in this picture. They are not at the same time. We can see that we can divide the lateral expansion into three regions based on temperature. There are the low temperature region, which is below the 1 kilokelvins, which is the preheated part swept by the oblique shock waves. And the transition region 2, which is between the 1 kilokelvins to 2 kilokelvins, which is formed because high temperature combustion products being heat absorbed by the droplets evaporation. And 3 is the high temperature region, which is a stable region formed after complete droplet evaporation. And there is basically no droplet evaporation inside the low temperature region, while almost all the droplets inside the high temperature region evaporated. So the droplets evaporation process mainly occurs inside the transition region. And when the temperature of constraint layer is 1 kilokelvins, like picture C, the temperature can rise above 1 kilokelvins just after the shock wave preheated. The low temperature region is formed by a large amount of gasification and heat absorption of high concentration liquid droplets. And there are the pressure and temperature distribution at different stages of different temperatures. We can also see the distribution of droplets in the pressure part, like this yellow part. So in the cell recovery stage, there is a low temperature region behind the detonation wave in the constraint layer, which is caused by the high local droplet concentration and strong evaporation with heat absorption. As the temperature of the constraint layer increases, the angle of the deflection at the same stage increases, and the distance required for droplet evaporation decreases. And now, as an example, here is the wave front analyzed with the 1 kcal constraint layer. We can see at 0.188 millisecond, there is an upward moving triple point and a transverse wave. The oblique shock wave has a larger inclination angle, and there is a protrusion near the constraint layer interface. At 0.19 millisecond, the transverse wave and the constraint layer began to interact. The leading shockwave surface produces a significant bend at the transverse wave position. At 0.192 millisecond, the transverse wave enters the constraint layer, leaving a local high pressure point at the bend. We can see that in the red circle. And the high pressure point gradually strengthens under the action of the reflected wave, transforms into a downward propagating milestone with a new triple point at 0.196 millisecond. And so here's the conclusions. When the constraint layer contains water mist, the detonation wave will extinguish faster due to the weakening of detonation waves caused by the evaporation and heat absorption of liquid droplets and difficulty in forming marked reflection. And two, the evaporation process of droplets and the temperature distribution in the constraint layer is, firstly, the oblique shock wave sweeps over the preheat and forms a low temperature region. Secondly, the combustion products push and compress the droplets, producing a localized high concentration droplet distribution and evaporating, forming a temperature transition region of 1 kcal to 2 kcal. Finally, the droplets completely evaporate, and the temperature tends to stabilize, forming a high temperature region. And now is 3. As the temperature constraint layer increases, the inclination angle of the oblique shock wave within the constraint layer increases. The transverse wave is more likely to propagate downward to the interface position, resulting in triple points and milestones. So that's all. Thanks for your attention. So how do you set the temperature at 500 and 1000 Kelvin? Do you only set the gas phase? It's much about the boiling point of water. You mean the droplet temperature? Uh, actually, actually, we made the temperature of droplets still 300 kelvins, and the time the evaporation naturally is much longer than the propagation of detonation wave, so it can be ignored. So the 500 Kelvin and 1000 is only the gas phase. Yes, that's it. Any questions?
So I can could you please explain again the background of the water waves from the detonation? Maybe at this stage.
Background.
Yeah, why this? Right. Okay.
Still have several minutes?
Anyway, one more. So what's the droplet size in your water mist?
It's 0.05 millimeters. Because it's a normal size of the water mist.